Welcome back. So last week we've seen how to encode the structure of a compact Lie algebra in successively simpler terms. First of all, we noticed that one can find a nice basis in a compact Lie algebra. So an orthonormal basis with respect to the Cartan killing metric, given by a set of Hermitian Cartan generators. And then the remaining vectors in this Lie algebra, they take the form of these vectors indexed by the roots of the Lie algebra. And the roots are exactly the eigenvalues of the Hermitian generators in the adjoint representation. And we notice that just by giving the set of these roots, so these are really vectors in the R-dimensional space, where R is the rank of the Lie algebra, one can completely retrieve the structure of the Lie algebra. One can further simplify this by noticing that it is sufficient just to have the simple roots among these roots to reconstruct the full root system. And then the simple roots are conveniently encoded in the Cartan matrix, which essentially just keeps track of the inner products of the simple roots. So that was quite the general story. What I want to do this week is to focus on how this additional structure of the roots allows one to find representations of Lie groups, and in particular SU3. So for the first 20 minutes or so, I want to focus on the general problem of finding representations given the root systems. And then we'll focus on SU3 and also on an application of these irreducible representations of SU3 to particle physics. Okay, but let's start just with a compact Lie algebra G. We have this basis of Hermitian Cartan generators and vectors or generators corresponding to the roots of this Lie algebra. And by construction, these generators satisfy these commutation relations, where the equation I write here is exactly saying that in the adjoint representation, E of alpha is an eigenvector of Hi with eigenvalue alpha I. But now we want to focus on more general representations, not just the adjoint one. So for this choice of basis, these commutation relations, they will hold in any representation by a definition of being a representation of a Lie algebra. So that means that in any representation, and let's say a representation in which the Cartan generators are still Hermitian, you can always use a similarity transform to make sure this is actually the case. So in any representation where Hi are Hermitian, well, they commute, so we can find this simultaneous diagonalization of these generators. So there exists a basis, and there exists a basis that's denoted in the quantum mechanical fashion, labeled by the weights mu. So these are the weights, which are again take values in the r-dimensional plane, and the x are some additional labels you need whenever these weights are degenerate. So the basis of this form such that the action of the Cartan generators on such a state diagonalizes it, and the eigenvalue is mu of I, mu x. Okay, so how about these other generators E of alpha. What can we say about their action on these states? Now we already touched upon this last week, and also in the case of SU2 we understood what the remaining generators actually do. They combine into raising and lowering operators. So they give rise to, okay, in this case there is not really a distinction between raising and lowering, because we're gonna rather, let's say, move around in the weight space. They give rise to moving operators, in the sense that if I look at the state E of alpha acting on this, that it is again going to be an eigenvector of the Cartan generators. Let's check this. We already did this computation last week in the adjoint representation, but it's true in any representation. So we use the commutator to switch the order of these operators. So we get E of alpha hi plus the commutator of hi and E of alpha, so plus alpha I of alpha acting on this state. But we know that this is an eigenstate of the Cartan generator, so what we find here is that this is exactly mu I plus alpha I acting on the state. Sorry, not this one, of course. We have E of alpha acting on the state mu. So this means that if this is non-zero, then it is proportional to a state which is an eigenvector of the Cartan generator with these eigenvalues. So it has weight mu plus alpha. Okay, of course we don't know in which of these states it will end up. Let me just write it like this, with a additional label x prime. Or, I mean, in general it will be a linear combination of all the states that have this particular weight. So E of alpha, what it does is it takes a certain state with a certain definite weight, and it just moves the weight by the root. So let's check in an example that we know now very well. So in SU2, remember that the Cartan generator by convention we take to be J3, the third generator. Now the eigenstates of J3 in an arbitrary representation, okay, we don't know, okay, we can have, it can decompose into many spin J representations, but we know that their eigenvalues are all going to be half integers, right? Or first let me say that the roots of SU2 they are plus or minus 1, with the corresponding generators being the J plus and J minus. So E1 is J plus, and E minus 1 is J minus. And if we look at the root system, so we have, this is the root diagram. So we have the root 1 and the root minus 1. So the corresponding generators are J plus and J minus. So in the spin J representation, we understand this very well. This is just saying that we have a certain number of states, say from minus J up to J, and these the generators corresponding to the roots, they just move us either down by -1 or up by 1. And so this is the j minus, and we also have j plus here. In a more general representation, you can have here a degenerate states, but we know that they will all be half integer weights by our classification. So how about some more interesting Lie algebras like SU3? Well, in the exercises you have derived what the root diagram of SU3 looks like. So it is of this form. Like this. So here I have the H1 axis and the H2 axis. You found 6 roots. So combined with the 2 Cartan generators, that gives you 8 generators, and SU3 is indeed an 8-dimensional Lie algebra. So that works out fine. So these are the roots alpha. So now in any representation of SU3, we have this basis of states, where now the weights are 2-dimensional vectors, so they also live in the 2-dimensional plane. So the weights in any representation, they live in the 2-dimensional plane. And if I have some weight mu with corresponding eigenstate mu, x, I now know that if I act with these the generators corresponding to the roots on them, they're going to move them exactly by the root. So let's see, perhaps if I act with this root alpha, then it will move it here. So this will be the result of a E alpha 1. But I can also act with it with a different root on it. So maybe this is alpha 2. So we'll move it there. Or I can use this one. I will move it down here. I can move back, if you like, using this root. Maybe I can go further up. Here, down there. Maybe I can go like this. So that means that these the weights in any representation, they're gonna form up into some geometrical figures. So the purpose now of this week's lectures is to really classify in what kind of shapes the weights of a representation can group up. Now before making this more precise, let me give a recap of SU3. So let's see whether we really understand this the root system here. Where do these generators sit in kind of conventional in a conventional basis of SU3? Okay. So let me do that up here. So let's recall the definition of SU3. So SU3, if you remember, this is the set of 3 by 3 complex matrices which are skew Hermitian, so x dagger is minus x, and traceless. So recall this condition, it corresponds to the unitary condition on the Lie group, and the traceless condition corresponds to the determinant equal to 1 condition on the Lie group. Then let me give you a conventional basis of generators. Generators, I can take them to be either skew Hermitian ones or the Hermitian ones, so I pull out a factor of I to make them Hermitian. And I'm also going to take a factor of 2 out of these matrices lambda A, which are the Gell-Mann matrices. Gell-Mann matrices. So let me quickly write them down for you. So these are the following matrices. Of course, I don't know them by heart, so I'll just copy them from my paper. So there have to be 8 of them. And it should not be too difficult to check that they really form a basis of the traceless Hermitian matrices. Like that. So they're orthonormal in the sense that if I take the trace of TA and TB, then they're normalized such that this is the case. So they're normalized with respect to the Cartan killing inner product. And given these explicit representation of the matrices, you can write down some structure constants for them. So if I compute explicitly the commutator of TA and TB, they will give you some explicit structure constants of this form. Where, well, because this gives you a orthonormal basis, these structure constants are going to be completely antisymmetric. Where the structure constants completely antisymmetric. Okay, I'm not going to write them down explicitly for you. But it's already relatively easy now from these explicit matrices to find a nice set of Cartan generators, because exactly 2 of them are diagonal. So they trivially commute. So by convention, the Cartan generators, there have to be 2 of them because it's a rank 2 Lie algebra, are taken to be H1 is lambda 3, so T3, and H2 is the last one, T8. So how about the other roots here? So let me draw this picture slightly larger. And we can just explicitly identify them. Let's draw the angles at least approximately correct. they're like this. So we have H1, so that is just T3. We have H2, which is T8. And then what are the roots? Well, they're just combinations of these, just like in the case of SU2. So this root, so this is root 1, 0. It corresponds to the following generator, 1 over square root of 2 of the first two matrices. So T1 plus I T2. And then similarly, the minus 1, 0 root corresponds to the other combination, so T1 minus I T2. Here we have the root 1/2 square root of 3. So these are all normalized, these roots of length 1. They correspond to the generator 1 over square root 2. Let's see, so T1, T2, and T3 are used now. Then we have T4 plus I T5. So here we have T4 minus I T5. Now then you can perhaps guess what I get here. Here I get T6 plus I T7, 1 over square root of 2. And here I have 1 over square root of 2. T6 minus I T7. And indeed, you can explicitly check with these definitions of H1 and H2 and the roots that HI, HJ commutes, and HI with E alpha is alpha I E alpha.